Hi class, we are on the next section, chapter 2.4. Today we're going to talk about exact equations. So this is the next approach that we use if our equations are first order and are not separable or not in a linear form as we saw in the last video. Okay, so the next approach would be to see if it's an exact equation. And this one's a little bit more robust. We have a couple of options to use if it fails, right? So after this section, we have one more approach, which we'll cover in the next section, chapter 2.5, for how to approach solving first order DEs. So an exact equation is a DE that we can express as a differential. Basically, some function in x, y that's equal to z. So if we were to differentiate this in terms of its partials, right, the differential d of z would be the first differential in x times dx plus the first differential in terms of y times dy when we differentiate this, right? So basically what's happening here is your function is differentiated in terms of x, and then you have basically an x prime type term, right? You get your derivative of this function in terms of y, and then you get your y prime term, right? So think about this like you would for implicit differentiation, right? For instance, let's say we're differentiating this in terms of y, so this is dy. This is partial in terms of x times derivative d of x, partial in terms of y times dy, and then we can get rid of that denominator partial that's common everywhere, and so we get this differential term, right? Here, if z is a constant, right, it's an r, then when I differentiate it, it's going to go to 0, which gives this to me as an equation that's equal to 0, right, an homogeneous equation. So I got the first partial of f with respect to x times the differential dx plus the first derivative of f with respect to y times the differential with respect to y, right? So here we can say that this function is a function which I would call m, right? So if this is a function in terms of x and y, then it's highly likely that there's still a y term here. So I will call this a function m that's in terms of x and y. Same thing for the first partial of f with respect to y. I would call that n of xy, right? So I'll give these a different name, and then substituting those in, I can write this in function notation instead of in partial derivative notation, right? Which may make a little bit more sense. I can also write it as f subscript x and f subscript y with its differentials, but it's a little bit easier if we just think about it in terms of functions that are there, right? And so when I add these things together, I should get out 0, right? So this is an exact homogeneous equation because there's no terms on the end, because here my z term was constant, right? It's an element of r. Note that if these second partials here are continuous over the same interval, then they are going to be equal to each other, okay? Or I guess I should say that the other way, that if the second partials, the mixed partials, are equal, then they're going to be continuous over the same interval, right? So if I do partial of x and then partial of y, and then do partial of y and then partial of x, and they're equal to each other, then they should be continuous over the same interval, which is very, very important. It's actually a requirement here. So if I were to take m, which is already a partial with respect to x, right? That's why it's the dx term, and I do it in terms of y, right? And I take my n function, which is already a differential derivative in terms of y, and I take its derivative with respect to x, they should equal each other, okay? If they don't equal each other, then I do not have an exact equation, and I have to move on to another process, right? Which we'll actually discuss in this video, okay? If I do have these things equal to each other, that's the condition necessary to be an exact equation, and then I can follow the rest of the algorithm, which we're going to outline right now, right? So our solution to this homogeneous equation here, right, is a constant value, right? It's not a constant value, but it would be set equal to a constant value. Basically, what this is saying is that that constant of integration that I get out, I will set my addition of functions equal to that. Okay. So let's go ahead and do an example. This is all very theoretical. It's always easier in a class like this when we do an example. So let's go ahead and solve this IVP that we have, right? Okay, so first and foremost, let's think about what we've done so far. Here, and in all of the forms that we've looked at, I don't really like the y prime. I like the dy dx form, right? So if I put this into dx dy form, if you try to separate this out, you'll notice that it's, again, not separable, right? So our first method of trying to solve would fail. I can't solve this by using the separation of variables method, okay? Next, if I try to put this into the the linear equation form, it's not going to work either. I'm not going to be able to get dy dx plus some function in x times y equals only functions in x, because as you can see here, the non-homogeneous portion has functions of y, and even here I have functions of y, so I can't put this into a linear form. Okay. Now normally you won't figure that out just by looking at it. You'll kind of approach it with the intent of trying to separate it, and with the intent of trying to put it into standard form or into the linear standard form that we saw in our last video, right? When both of those things fail, then you would attempt this. However, we're already in this section, so we know that that's the approach we have to take, because all of the questions in this section are going to be in some kind of an exact form, right? So I'm going to approach with the idea that I already know it's an exact form. However, on an exam, you may have several equations and you need to figure out, is this a separation of variable? Is this a linear equation form? Or is this an exact form or some other form that we haven't covered yet, right? So again, the form dictates the approach that you use to solve, right? So can't separate it, I can't put in linear form. I need to look at the partials, right? My requirement for this being an exact equation is that if the second order mixed partials are equal to each other, right? So I need to check that condition, because I already know, again, it's not separable and it's not linear. You can also tell it's not linear because there's a nonlinear term here, right? So it's obviously not a linear equation, right? E to the y is the nonlinear term. Y times e to the y is the nonlinear term, I should say. So I replace y prime with dy dx, right? And then I start to separate my dy dx. So even just looking here, it's very clear that I would not be able to separate this. It's the same step as I would take for separation of variables, but it's very clear I'm not going to be able to get all the y's on one side and all the x's on the other side, especially with these mixed functions times my differentials, right? It's just not going to happen. So what I want to do is I want to check these functions, right? So let's first put it into standard form. So my function times dy plus my function times dx, all on one side and 0 on the other side. This is that standard form that I'm looking for these exact equations, right? So I'm going to move everything over, okay? So here I can pull out the common negative, so that's really just me adding it over. I'm not multiplying, right? I'm adding this thing over. So I have this positive term times dx plus this term times dy equals 0. And now I'm in this form. So the one that's multiplied times my dx, that's my m function. The one that's times my y, that's my y function. So what I need to do is I need to take my m function, right, the one that's times dx, and I need to differentiate it with respect to y. I need to take my y function, right, the one that's times the differential in term of y, and I need to take its partial derivative with respect to x. So we can do this really quickly just by looking at this. We'll write it out, but we can look at it. If I take this and I differentiate it with respect to y, this is held as a constant, so it goes away, and this turns into 1. Here, with respect to x, This is held as a constant and goes away. This is held as a constant and goes away. And this goes to 1. My mixed partials both equal 1, and they're equal to each other. So it satisfies the condition for being an exact equation. So then I can start to solve this as an exact equation, right? So let's go through that verification, right? So this was my m function. This was my n function. When I take their mixed partials, for this one I get 1, right? When I take this derivative with respect to y, with respect to x, I also get 1. They're equal to each other. Therefore, it's an exact equation. So now I can start to solve, right? We didn't really talk about how to solve these, but we kind of did, right? We're saying that if I have this function in terms of x and y, and I take its derivative with respect to x, it looks like this, right? Or my m. When I take its derivative with respect to y, I get my n function. So really what I want to do, if I want to solve it, I need to undo this differentiation. So I'm going to integrate this with respect to x to undo that derivative with respect to x. And I will integrate this with respect to y to undo that integration with respect to y. Now you have to do both. You can't do just one, right? Because if you do just one, the function you get may be missing some terms from what may have happened here when you differentiate with respect to y. Maybe something fell out and completely disappeared. So when you integrate this with respect to x, it might not show up because this is all with respect to x, whereas this is with respect to y. So whatever function may have disappeared or whatever may have happened, it might not be captured here when you integrate with respect to x, right? So to reiterate, I need this function such that its first partial with respect to x equals my m function, and its first partial with respect to y equals my n function, right? So it makes sense that I integrate this with respect to x, okay? So I'm going to integrate this with respect to x here, right? So I'm going to get just e to the x, and this is going to turn into xy, right? Plus g of y. So again, this is just it's not a constant of integration, but it is a constant of integration, right? It is taking care of any function of y that may be missed, like I said, from this differentiation here, right? So when I differentiated my original function with respect to y, it's possible that something disappeared. So my constant needs to be not just a constant, but just some generalized function with respect to y so that I can incorporate it in. So what I'm going to do here is I'm going to do the same thing here. I'm going to take this n function and I'm going to integrate it with respect to y, right? And then I'm just going to equate the two together, right? Because the integration here plus this integration here, there should be some overlapping terms and possibly some new terms, and those new terms are those g of y functions, right? So what are you saying, Professor Williams? Well, let me show you, right? So let's integrate this with respect to y, okay? So this will turn into 2y, this will turn into xy, and then here we're going to have to use some of our nice cool methods we have for integration, right? So this is a function times another function, so that's going to require integration by parts. Now I do integration by parts a little bit different. Maybe you've seen it, maybe you have not. Most likely probably not if you're at my campus. We don't really teach it this way. So instead of using the UV, DV, whatever formula, I can't even remember what it is, I use what's called the tabular method or the Tabular Method. Super easy to remember, super easy to use, okay? I'm going to pick some function out of this to differentiate, and I'm going to pick some function out of these two to integrate. Now, the one that I choose to differentiate should be whichever one ends up going to 0 when I differentiate it. So, ideally, this y, okay? The one that I choose to integrate is the other one, right? There's only two, okay? So what I'm going to do is I'm going to differentiate this y here until it goes to 0. And as many times as I differentiate this y, I'm going to also integrate this e to the y, right? Now what's going to happen is as I do this, I'm going to have a multiplying factor that oscillates, right? It alternates between positive, minus, positive, minus, positive, minus, positive, minus, as long as I'm doing my integration and differentiation, okay? So when I do this, I also need to multiply my terms diagonally, right? So it doesn't make sense once I get through everything. So this is going to alternate between plus, minus, plus, minus. It always starts off with plus. I'm going to start off with the function that I'm deciding to differentiate, and I'm going to start this off with the function I'm deciding to integrate. So again, the one I'm differentiating has to go to 0, okay? So the first derivative is 1, and then the second derivative is 0, right? Here the integral of e to the y is just e to the y, e to the y, e to the y, okay? Notice here that this is going plus, minus, plus, minus, okay? And now these arrows go diagonally to indicate the term, right? So the product of these times the sign creates the term that I have, right? So this y e to the y will be y e to the y minus 1 times e to the y plus the integral of 0 times e to the y, right? Which is nothing, so that's why I choose this one to become 0, right? So this portion of the integral is y e to the y minus e to the y. So this result will turn into 2y plus xy plus y e to the y minus e to the y plus c. Okay, so right here, these two terms is what's coming from this table method. It's very, very easy to use. You pick one, you differentiate it. The other one, you keep integrating, and then you multiply across, and then the signs alternate in sign. Very, very, very simple to use. You don't have to remember u, dv, uu, or whatever that formula is that I never, ever remember. Okay, so this is my integral, right? This is the result of my integral. So notice that if we equate the two results, the integral of m and the integral of n, a lot of it is the same. I have e to the x, which doesn't show up here, but I do have an e to the y, right? I have a y times x, or x times y. So the g of y, constant of integration here, is picking up all the pieces that did not show up in this integration. So my solution is all of these plus all of these except for anything that's the same, right? So I don't need y to the x or y times x and y times x twice. I don't need that term twice. I just use one of them, right? So when I equate my two results, right, e to the x plus y to the x equals this stuff, right? This xy and xy here, they don't cancel out. I just use 1, right? I need them to be linearly independent, basically. So I'm not using any doubles, okay? So my g of y function, right, is going to be anything that didn't get picked up in the first integration. So that y e to the y, that negative e to the y, that 2y, and the c, right? My m function that I integrated has this that doesn't show up when I integrated my n, and that's about it, right? So I'm taking all the pieces of both, none of the ones that I repeat, and I put them together to create one function. So I have my e to the x, my 1y times x, I'm not using the other one, right? I have my y times e to the y, I have my negative e to y from the n function, I have my 2y, and remember, c is what it's equal to because it is an exact function. I assumed I had z equals a function, and since it was equal to 0, I assumed that z was a constant, right? So my solution is some function in x and y equaling that constant value, okay? Here we go, right? So that's my final answer, right? And you can always check. If you're like, well, I really think it should be 2xy, Professor Williams, or I think there should be no xy's because they're equal to each other and cancel out. Well, okay, if you don't believe me, then again, you can always check, right? So let's take our function here and integrate with respect to x. I should get e to the x plus y. So I'm going to get an e to the x, right? Y here is being held as a constant times x, so it turns into y when I differentiate. this is in terms of y only, y only, y only. So all of these go away, right? So if I differentiate this with respect to x, then I get e to the x plus y, which I do. If I come over here and I hold x as a constant and I integrate with respect to y for my function, this goes away. This turns into x, which I have, right? My 2y, the y goes away and the 2 stays, right? And then here, this disappears when I differentiate this, right? So when I differentiate this, right, with respect to y, I'm going to end up doing the product rule, right? So I'm going to get 1 times e to the y plus e to the y, y times e to the y. So the y times e to the y term will stay, and then the first part, the 1 times e to the y, so just e to the y, will cancel with this, and that will disappear. And so I'll be left with just y e to the y when I differentiate this with respect to y, right? So this actually works out. Okay, and we do that again on the next slide. So let's go to the next slide. So quick slide. When I differentiate with respect to x, I get this. When I differentiate with respect to y, I get y times x gives me this. The 2y turns into this. I get the product rule with the derivative of e to the y, which is just e to the y. So those cancel out, right? And I'm left with x plus 2 plus y e to the y. Right? So when I plug in my initial value condition to my solution here, right? So I'm plugging in 0 here, and I'm setting it equal to 1. So I plug in 0 everywhere, okay? And everywhere I see x, I plug in 0. Everywhere I see y, I plug in 1, right? E to the x is 0. X times y is 0 times 1. Y e to the y is 1 times e to the 1. So here, all of that is going to be equal to that constant that I have. So I'm going to be left with 1, 0. This is going to disappear, and I'm going to get 2. So 1 plus 2 is c, or c is equal to 3, right? So therefore, my exact solution is this solution equaling 3, okay? So now you can see everything in one place. If you think about this being differentiated with respect to y, this is the result you'll get out, right? X and y is here. The 2y is the 2. This comes from differentiating this product rule, and this negative y is just, it stays the same when you differentiate, right? So there we go. That's our exact solution, right? For non-exact equations, we can sometimes find an integrating factor. So I know it says sometimes, but it's actually a lot of times. So I don't want you to think that it's not very often. It's actually quite often that you can turn a non-exact equation into an exact equation, right? So here our integrating factor is called mu of xy. So here our integrating factor is a multivariable function. It's a function in x and y, not just x, right? Actually, it is just x or just y, but we consider it multivariable. So it works the same way, right? So there's some conditions for figuring out if it's a function in x or a function in y. Okay. However, the nice thing of figuring out how to use our integrating factor is that I use the results that I had from trying to figure out whether or not my equation was exact or not. So I already end up finding these values when I try to figure out which integrating factor I'm going to use, right? So basically, if I take my m function after I've differentiated with respect to y, and I subtract my n function, that's a partial in x, by my n function, right? That's already a partial in y, right? So not the mixed partial, just the single partial, right? That f of x y function with respect to y. If this result is only a function of x, then this is the integrating factor we use. We use that result raised to the power of e and took in the integral of, right, with respect to x. If I mix this around a little bit, right, if I mix the order and instead of dividing by n, I divide by the m function, if that is only a function of y, then we use this integrating factor. Okay. Now, um, if neither of these results is just a function of x or just a function of y, if neither of these conditions are satisfied, then we cannot make our function an exact equation, right? It is a non-exact equation, and we will not have an integrating factor that will work for it, right? So this is how we change it into an exact equation if it is not an exact equation. But again, this does not always work, but it does work a large variety of the time. Okay, so let's do an example. Here I have 3xy plus y squared plus x squared plus xy times y prime. So again, I'm trying to throw you off with the notation. We're going to want to use that dx dy notation because that is what we need here for this partial form, right? So let's come back here. Okay, so first thing I'll do is I'll write this as dx dy, and then I'll split it apart by multiplying everything by dx, right? So I'll cancel the fraction here. That will put into a dx dy form, right? So as you notice, as we go through this course, I'm running a little bit less and less algebra because your algebra should be extremely strong at this point and you should be able to follow. And we've already done an example where we kind of went through everything step by step by step, right? So I'm going to take a few little liberties here. They're not huge jumps, but they are, you know, a little bit of a step. You should, like I said, be watching this video with a pencil and paper and kind of doing some math as we go, right? So here, this is my m function because it's with the dx, and this is my n function because it's with the differential of y. So what I need to do is I'll just write those things down, right? This is m, and that's n, okay? I need to take my x function and do its second partial for the other variable, right? So since this is already my original function being differentiated with respect to x, I want to look at what it looks like when I differentiate with respect to y. I'm going to do the same thing here. I'm going to write the mixed partial. Hopefully they're equal, and if they're not equal, then I'm going to figure out which kind of integrating factor to use, and hopefully that works as well, right? If it doesn't work, then we would approach with a completely different method, right? So we would go, oh, it's not separable. Oh, it's not linear. Okay, it's not exact. Okay, my integrating factor didn't work. So now I'll try, boom, whatever it is that we're going to see in the next section, right? Chapter 2.5. So here I'm going to differentiate this with respect to y, right? So here the y goes away. This turns into 2y. I'm going to differentiate this with respect to x, so this will turn into 2x, and then the y will be left over. And they're very, very close to being the same, but not quite. Okay, they're not the same, so this is not an exact equation. So since it's not an exact equation, all hope is not lost. I want to see if I can use an integrating factor. So now the question is, well, which one do I use? U of x, or I'm sorry, mu of x or mu of y? Well, in order to figure that out, I need to look at these relationships. So I have my m sub y, my n sub x. I have m, I have n. I just kind of got to throw it together. A lot of times you can really just look and say, oh, okay, yeah, these cancel out and there's only x's. Oh, these cancel out and there's only y. Or, oh, nothing's going to cancel out. This is a mixed function in x and y. There's nothing I can do, right? So here, nx minus my, I'm going to get 2x minus 3x, right? So I'll have a negative x and I'll have a y minus 2y. So the y's don't cancel and the x's don't cancel, and then that's over m. So hopefully maybe something cancels by factoring. So let's see what we get. Okay. So here I factor out y on the bottom. I cancel out the things I can cancel. Nothing cancels out. I have a mixed function in x and y. So my second condition is not met. My integrating factor would not be this form. Okay. That does not mean automatically that this is my integrating factor, because it could be very possible that I don't have an integrating factor at all, right? So you can't jump to conclusions. We have to check. So if I check the my minus nx over n condition, I will have 3xy plus y squared minus x squared plus xy, right, all over my n function. Oh, I'm sorry, I'm subtracting these two. 3x plus 2y minus 2x plus y all over x squared plus xy. So here I get x plus y over, when I factor out the x, well, look at that. I get something that cancels. So this is 1 over x. So it's a function in only x. So I can use mu of x. So I'm going to go e raised to the power of the integral of 1 over x, right? Which is nice because that is actually going to be e natural log of x. And e to natural log of x is really just x, since e and natural log cancel, right? So my integrating factor is very, very nice here, right? So when I use this integrating factor on my original equation here, I'm just going to multiply this term by x and this term by x. So 3x squared, xy squared, x cubed, x squared y. Right? 3x squared y, xy squared, x cubed, x squared y, right? So I just increase, and now my equation is exact, right? So we can check just to make sure we're on the right path, right? This is my m function. This is my n function. This derivative with respect to y is 3x squared plus 2xy. This function with respect to x, when I take the derivative, is 3x squared plus 2xy. They're equal to each other, right? Therefore, my equation is now exact, okay? So when I integrate my m function with respect to x to try to get back to my original function, so again, remember y is held constant, and I'm integrating my x. So here, this will jump up to x cubed, and 1/3 times 3 will cancel. So this will be x cubed y, and this will turn into 1/2 x squared y squared, right? So I put my function in, and when I integrate it, I get this out plus that constant of integration, right? So next I need to integrate my n function with respect to y, okay? So I take this and I plug it in, right? And so when I integrate this, this will be 1/4 x to the 4th. I'm sorry, with respect to y. So this turns into x cubed y. This turns into 1/2 x squared y squared. So you notice I have two terms here that will be identical, right? These are the same and these are the same. And my g of y will just be that constant of integration. So again, I don't rewrite, I use all the parts that are different. I don't use the parts that are same. So my function is going to be x cubed y plus 1/2 x squared y squared equals c.